Hello, welcome to another module in this massive open online course on probability and random variables for wireless communication. Today we are going to start with a new topic, that is a concept of a continuous random variable. So we are going to start dealing with the notion of a random variable, which is an important concept. So we will start dealing with a random variable, and a random variable can take, basically as the name implies, can take values randomly. So a random variable x, if x is a random variable, x is a random, if x is a random variable, then x can take values randomly from either the entire set of real numbers or a subset of real numbers. So x, which is a random variable, can take values randomly from entire or subset of real. So x is a continuous random variable. It can take values randomly from the set of real numbers, and this random variable x is characterized by a very important function. This is known as the probability density function. This is characterized by f of capital X. The subscript capital X denotes the random variable. The small x denotes the value of this probability density function at a particular point x. So this is the probability density function of, this is the probability density function, also denoted by PDF. This is the probability density function or PDF of the random variable x, PDF of the random variable x. PDF of the random variable x. And what does this PDF, probability density function of the random variable x, what does it denote? What does the probability density function of this random variable x denotes? Let us consider a small interval of width dx around x. That is, let us consider the small interval between x and x plus dx. So let us consider the small interval between x and, let us say this is the PDF. Let us consider the small interval, infinitesimally small interval between x and x plus dx. So this is my point x, this is my point x plus dx. We are considering an infinitesimally small interval of width dx. This is my probability density function f of x of x. Okay. So we are considering, so consider an infinitesimal interval x comma x plus dx. That is, we are considering an infinitesimal interval of width dx around x, that is the interval between x and x plus dx. Then the quantity f of x times dx. Then if we look at this quantity f of x times dx, this represents, this is the probability that random variable x lies in the interval x and x plus dx. X lies in the interval x to x plus dx. So, if we look at this infinitesimal interval, x between x and x plus dx, the quantity f of x times x dx. So, the quantity, so the probability density function is f of x correct, and f of x times dx basically at a point x denotes the probability that the random variable capital X takes value in this infinitesimal interval of width dx, that is in this infinitesimal interval around x, which is the infinitesimal interval x to x plus dx. So, f of x times dx is represents the probability that the random variable takes a value in this infinitesimal interval. So, that is the significance of this probability density function. This is the significance of this probability density function. It denotes the probability, but it is not straightforward, that is f of x is not the probability, f of x times dx, that denotes the probability that it takes a value in the infinitesimal interval of width dx around x. And naturally, since f of x represents the PDF, represents a probability, it must be the case that f of x, since probability cannot be 0, f of x has to be greater than equal to 0, that is the PDF, the probability density function, PDF stands for the probability density function, is greater than or equal to 0 for all values of x. At any point x, the probability density function has to always be greater than or equal to 0. It cannot happen that the probability density function is negative for a certain value of x. Okay. So, the probability density function represents the probability density of the random variable x, which when multiplied by dx gives the probability that the random variable x lies in the infinitesimal interval around small x, that is lies in the infinitesimal interval between x and x plus dx. Also, this naturally means that therefore, now the probability that x lies in this interval, if we consider any interval a b, probability that x lies in this interval a b probability x lies in this interval a b is basically, now if you look at the probability density function again, the probability, this is the probability density function f of x, and now let us say I am considering this interval between 2 points a and b. The probability that this random variable lies in the interval a to b is the area under the probability density function between the points a and b, that is equal to integral a to b of f of x dx. Therefore, what we are saying is that the probability that the random variable x lies in this interval between a and b is the area under the probability density function between these 2 points a and b. Therefore, the probability, I can talk about the probability of x random variable x, which is a continuous random variable, that is it takes values on the real line. The probability that x is element of a times b is equal to integral of a to b f of x of dx, which is the same thing as saying that the probability x element of a b is basically this quantity. If you can look at this quantity a to b of f of x dx is basically nothing but the area under the probability density function. This quantity is basically area under the PDF, that is probability density function between the points a comma b. So, if I look at the interval a comma b, the area under the probability density function between these points a and b, that is integral a to b of f of x dx, represents the probability that the random variable x is element or belongs to this interval a or b, between a and b, or that the random variable x takes values from this interval on values in this interval a to b. Naturally, therefore, it follows that further naturally, I am saying naturally because it follows from the above result, naturally if we consider integral minus infinity to infinity f of x of x dx, that must be equal to 1. If I consider the integral from between the limits minus infinity to infinity of f of x dx, where f of x is the probability density function, this integral over the entire set of real numbers must be infinity, because the entire set of the real numbers is the sample space. It is a sample space for this random variable. Therefore, the probability that it takes any value from the sample space must be 1. The total probability that it takes any value from the sample space must be equal to 1. So, what we are saying is, for this random variable x, the sample space equals minus infinity to infinity. Therefore, probability, so what we are asking is, this is basically integral over minus infinity, integral minus infinity to infinity f of x dx is basically the probability that the random variable x belongs to minus infinity to infinity, which is the same as the probability that the random variable x belongs to the sample space, which is equal to 1. Because this is basically this quantity, as we have seen in the axioms of probability before, this quantity is basically the probability of the sample space, and from the axioms of probability, that is from the second axiom of probability, we have the probability of the sample space is equal to 1. Therefore, the total area under the probability density. So, we have two interesting properties. One is that the probability density function f of x is always greater than or equal to 0, and two, the area, the integral between minus infinity to infinity of f of x of dx. And what is this? This is the total area under the probability density function on the entire real line between the limits minus infinity to infinity. This total area under the probability density function must be equal to the total probability, that is unity. So, the total area under the probability density function, what is this quantity? This quantity is the total area, this quantity is the total area under probability the total area under the probability density function must be equal to 1. We are saying that the total area under the probability density function must be equal to 1. So, the probability density function is greater than or equal to 0, total area under the probability density function equal to 1, and f of x times dx represents the probability that the random variable x takes a value in the infinitesimal interval of width dx around x, that is it lies in the interval between x to x plus dx, and integral a to b of f of x dx is basically the probability that the random variable takes values in the interval a to b, all right. So, for example, let us take a look at this simple example now. Let us take a look at this simple example. For example, let us take a look at, consider the PDF f of x equals k e to the power of minus ax for x greater than or equal to 0. That is, we are given a PDF which is k, some constant k, times e raised to minus x for x greater than or equal to 0, where a is a known constant. A is also termed as the parameter. This quantity a is also termed as the parameter. A is the parameter of the this PDF, that is the probability density function. And what we are asked to do is that we are asked to find the value of the unknown constant k. So, we are given a PDF which is k e to the power of minus ax, where a is a known parameter. This PDF is valid for x greater than or equal to 0, and what we are asked is, what is the value of this constant k, and naturally we can find it as follows. We know that the total probability is 1, therefore it must be the case that if I look at the total probability, this is defined from 0 to infinity. So, therefore, if I look at the integral 0 to infinity, of f of x of for a general PDF, it is minus infinity to infinity, this must be equal to 1. However, this is defined only from 0 to infinity. So, it means that from minus infinity to infinity the PDF is 0. So, 0 to infinity k times e power minus ax dx is equal to 1. Now, this integral k times e power minus ax, this integral, you can evaluate this integral in a straightforward fashion. This is minus k over a e to the power of minus ax evaluated between the limits 0 to infinity, which must be equal to 1. It means, now if I substitute these limits at x equal to infinity, this is e power minus ax, which is e power minus infinity, this is 0. So, therefore, this is 0 minus of, at x equal to 0, e power minus ax is e power minus 0, which is 1. So, this is 0 minus of minus k by a, which is equal to k by a, and this is equal to 1, implies our parameter k is equal to a. So, k, we derived that k by a is equal to 1, which means our parameter, remember our PDF is k e power minus ax, right, using the probability that the PDF must be integrated to 1, that is the area under that PDF over the entire real line is 1. We have derived the condition that k is equal to a, therefore, the PDF is given as therefore PDF is f of x which is equal to, k is equal to a, this is equal to a e to the power of minus ax for x greater than or equal to, which is basically for x greater than or equal to 0. So, let me write this again clearly over here. F of x equals a e to the power of minus ax for x greater than or equal to 0, and this PDF which is decreasing exponentially, this PDF looks like this. This PDF for a is constant, it is decreasing exponentially. This is a e to the power of minus x, this is x, this is f of x, it is decreasing. A e to the power of minus ax is basically decreasing, it's basically decreasing exponentially. It starts with a at x is equal to 0, and it is decreasing exponentially at x equal to 0. This is basically a e power minus 0, which is a, and it is decreasing exponentially. This PDF is also known as, this is known as the exponential PDF. This is known as an exponential PDF. This is one of the standard probability density functions. This is known as an exponential probability density function. So f of x equals a e power minus ax for x greater than or equal to 0. This is the exponential probability density function, and we have also seen that this a is a parameter. This a is a parameter which characterizes this exponential probability density function. So we are saying that this probability density function f of x equals a e to the power of minus ax is the exponential probability density function. It is defined for x greater than or equal to 0, all right, and a is the parameter which characterizes this exponential probability density function. So in this module we have seen a definition of the probability density function of a random variable, the properties of the probability density, what it represents, the probability density function, the properties of this probability density function, and also we have done a simple problem involving this exponential probability density function. So let us stop this module here, we will look at other aspects in the subsequent module.